On the last episode, I didn't do anything particularly controversial. It was a straightforward tech demo where we modeled up a building. Now we're going to do some solar analytics on that. Long time ago in a galaxy not too far from here, an age before computational designer existed as a job title, I was an architectural graduate. The office I was working for at the time made an attempt to transition to Revit, but they failed. So that meant there was no 3D model. As the Rhino guy, it was my job to take the 2D drawings produced in AutoCAD and turn them 3D. Not sure what the demographic data is for my audience, but for all you young folks that were still in nappies back in the CAD age before there were BIM models, architects had to manually project out lines from the plan to make sections and elevations, which was always tedious and prone to human error. When I imported the DWGs from AutoCAD into Rhino, all the history on the CAD blocks had come through too, so it was a nightmarish mess of lines that if taken literally all the way to construction would have produced something like this. But during the gaps between these modelling tasks, I had time to build a Python code to automate this. Of course, I still had to manually trace the plans, but if I put the objects on the right layer, the code could 3D it for me. I got a process which previously took me weeks or days, down to days or hours, depending on the size of the development. Once the geometry was three-dimensionalated, I'd hand over the models to the visualization team to make renderings in 3D Studio Max. Looks like AI already just about killed off that job, but I was also responsible for solar analytics. I don't know where you live, but in New South Wales, such a stupid name for a state, I wish they'd change it.
There's nothing like North Wales. No, South Wales, of course.
The apartment design guide enforced that at least 70% of apartments in a new building should have at least 2 hours, or 3 hours outside of Sydney, sunlight per day on the winter solstice between 9 AM and 3 PM. Back then, we didn't have Ladybug. I inherited a dodgy process in 3D Studio Max, which was really inefficient because I had to convert the models over and make sure that the origin was all aligned, and it was a nightmare. So I tried to recreate the process in Rhino. The script would take a series of 3D snapshots, 3D views, as though the camera where the sun is looking at the building at the angle at each time of day. If you could visually see the windows of the living room, you would stick a little number on it. Then I had to go through and manually count all of these up. So if you had a 0 at 9 o'clock and a 1 at 10 o'clock, and that's all you get, then that would be 1 hour of sun. Sometimes I'd come back from this process and I'd be like, "Good news, boss, we got to 85%. And then the boss would be like,
"Oh, that's no good. We'll try and squeeze a few more in then to keep the developer happy."
And other times it would be like, "Bad news, boss. We couldn't get it to more than 60%. Looks like your client bought themselves a dud of a block of land."
"No, my beautiful design."
One time we were testing a design and found that by changing the setting on the camera, you could visually alter whether the window was visible or not. To check, I got the line of the sun angle vector and attached it to the window, and it did indeed intersect the building. Take that, Owen! The design fails.
"But I want it to work, my precious. Change the camera back so it looks okay."
Oh, I get it now. Here's a fundamental difference between our personalities, boss. You want reality to bend towards your desired design outcome, and I want the design to adapt to reality so humans that actually have to live in these apartments actually get enough sunlight. Are you asking me to lie so it conforms to the fantasy world in your head, or how the sun actually works according to laws of physics? Years later, I revisited the idea by building the solar analytics into the Archistar platform. As far as I can work out, it hasn't been updated since, but I could be wrong. Ben, Cam, anyone want to fact check me on that one? So here we are almost a decade later. Don't currently have an architecture firm with any real projects. What I do have is a lot more BIM knowledge, Ladybug, and the ability to build my own Grasshopper components. Here we go. Now, for those of you who didn't watch the previous episode or need a reminder of what we did, we started with some lines, and we used some components I built in Grasshopper to convert those over to special Rhino blocks. These were then used to generate Revit elements. The two were then tied together so that if you update the Revit model, it'll automatically update the Rhino model and vice versa. And the result of all that was this butt ugly apartment building, which looks like one of the ones we have going up in Sydney all around us. I take no responsibility for the aesthetics at this point. It's purely for the purposes of solar analytics and spatial planning. We can make it pretty later. Now, of course, no building exists in a vacuum, so I've drawn up some context. Now what we have here is, this is traced from some 2D line work from a previous project, but I just made up the building clients, and I've got a park and little row houses and some other big blocks. This should block off some of the apartments for the solar to demo how that works. Now, since no building is ever truly north, south, east, west, but we don't want to be drawing an awkward angle, all the walls are orthogonal, but I've put in this north point. So this time I've color-coded the groups to make it a bit easy for you to follow. Let's start with Ladybug. So we're going to get this data here for the Sydney Airport as our starting point. This feeds in here to get the EPW, the location, you can get all the kind of data you need from there. And for this one, for the analysis period, we plug in the start month, start day, start hour, end month, end day, end hour time step. So that is for the winter solstice, which will be the worst time of year where we'll get the least amount of sun. So if it works on that day, it'll work on any day. Alright, that gives us the sun path. Okay. And next we're going to set a point to start the analysis. So just put it in the front of the building there. Okay, so if we were to turn the preview on with that, that's what the sun would look like if everything were perfectly north, south, east, west, but of course we know that it's not. So what we do is we get this line and that line, measure the angle, which is close to 7 degrees, plug that in here, we rotate around the z-axis, and that gives us this, which is slightly off. So this is the one we'll use. Next comes grid convergence. So if you look at Parametric Monkey, he has a great explanation on how this works. I'm not going to go over it, but it's, just something to do with the curvature of the Earth. Or alternatively, we could let Randall Carlson explain.
Then when you get up to the pole itself, when you're 1 degree away from the North Pole, you only have to go 1.2 miles because those meridian lines have converged.
Okay, now if we load up this government website, because we definitely trust that the Australian government is going to spend our tax money wisely and not spy on us, then we can put in these numbers. Luckily my browser remembers, so I don't have to actually type anything in. Submit. Here's our number, 102,413. Okay, or alternatively, I've got this little bit of Python here. Somebody already made this package called Redfan, so if you just download that and then you can plug in those same numbers and just get the dictionary of the grid convergence, then you get the same number. Then you don't have to go to the government website.
So it's not a perfectly square unit, is it? It's a little bit distorted. Well, that distortion is totally significant because it's that distortion that is a measure of the Earth's departure from being a perfect sphere.
Alternative history is so much more fun than actual history. In Rhino, views that we save are called named views. So if we go here, set view, named view, save it, new view, and then we go back to perspective, change it, then if we click new view. However, I don't want to have to bother doing that manually and trying to set it to the sun when I can automate that process. So now we come to the first of today's custom components. Okay, we feed through the vectors and the start location and the length. We can create some lines. So that will then create the camera location and the target location. And we also have a sample view, so in this case perspective, which is what we base the view on. And just a little bit of C# here to give the views a name and a location. Feed that through, hit run. Cool, and it's made them. So now if we go to our main views, then it's made one for each hour of the day. Okay, now we have another custom component for exporting the named views. So we've got the names, we've got a folder to put them in, and switch that to true. See, these components are the kind of thing that's a fairly low-hanging fruit. It's not that hard to code up, but there's nothing quite like it off the shelf, certainly nothing that has a for loop inside that can handle a list of items. A couple of years ago I was working at a company where I proposed doing this, and I didn't get a green light to do it, and instead the company was still using these horrible spaghetti graphs where you had to manually put in all this data and then manually name the files, and if you got that wrong and it caused some kind of problem. It's not that hard a thing to automate, just do it. However, if we go back to our old friend the New South Wales ADG, what it actually says is 1 meter squared of direct sunlight measured at 1 meter above the floor level. So whether you can see a window or not is totally irrelevant. That's why we used Ladybug. One of the annoying things about preparing a model for analysis with Ladybug is that you need to have single plane breps, whereas most of the architecture software works with solid breps. So that's why I built this tool here, which extracts a geometry. Alright, so if I get the sublayer objects of the building elements, that's all of them, and I set multiple objects to the block, and I let that run. Okay, and if we just switch that off, it's now sorted them depending on the parameters I put, like whether it's external or internal. So there's the external, there's the internal, we have, that one's empty, we have the floors, we have the windows, and we have the window frames. But for the first part, we just want to have the external and the internal walls. So these get merged together over here. The next problem we have is that since we're taking the planar breps, which are part of those solids, they don't always meet up nicely. So you end up with these little gaps. So that's why I've built this other node here which closes those gaps. And you can kind of change these parameters around to get that right. Okay, so if we switch that on and we switch those off, the new breps we have are closed. So we have a properly closed model. For the most part, it's not going to be 100%, but it's close enough for our purposes. We're going to combine that with some of the other geometry, such as the frames and the floors. And we're also going to get the context buildings, which is these ones. So that's going to form all the kind of stuff that's going to be shading the surfaces that we're going to be analyzing. Now the surfaces we're actually analyzing, they're going to come from the room breps themselves. Okay, so if we go down here, we have another one which is going to get our rooms, which is these ones here. So those 3D solids, and if we have a look here, if we turn that back off. Alright, so for now we're just getting the first floor. In parallel with the actual geometry of these breps, we're going to have the name of the room all sorted into nice trees, and in parallel we're going to have the type of room it is and which apartment it belongs to. Now next thing we're going to do is we actually only want the living rooms, just these ones, because that's all the law actually talks about in New South Wales. Okay, if we try and run this into the Ladybug out of the box node, yes, it does the analysis, and you can see the graph it produces. However, this is all one mesh. So all the kind of data we had, which was disambiguating which living room was which, is gone because it's all been flattened. Now if we try and turn this geometry into tree access, well, it just has an error. It's not expecting that, it's not built for that. But these nodes are just Python. And it's all quite open source, so it's not that hard to edit. So what I've done is I've copied that in and I built it so it can take a tree. So what we do is we still in here, okay, we have a nested geometry list, and that is produced by going through the geometry.branch count, getting the branch at I, appending it to a list, appending that list to a list of lists, and also creating a list of meshes and a list of results and a list of points. From there we go through here and we append to the mesh list and the point list and the result list what we need. And then down the bottom we have the graphic container which does the legend. Okay, so we have vectors coming through, same as before as a list. Time step, geometry is the room bases, context is the building elements and the surrounding buildings, grid size, offset distance, legend parameter, CPU count, and run. What do we got as a result? Looks the same, but what looks different is the way the results are structured. Now we have a tree structure which has sets of numbers which correspond to each one of these meshes separately. And the meshes are coming through in that list.
Hello, I'm an environmental activist and I'm going to be gluing this grasshopper to this data tree until somebody gives Mike a job in sustainability.
Okay, so what are we going to do with that data? Well, all we need out from this node is the results and the mesh. We don't actually need the points. And we're going to feed that through into another custom node which analyzes the solar results. So we have a run for true, we have the start time and end time, the results, meshes, and here we have names, types, room groups, and compliance. So names, types, and room groups, well, that's coming out of here, so the same branch structure we had when we extracted from the room bases. As for compliance, this is where we set what the rules are. So in this case, I've constructed some rules just with 3 panels, so they run in parallel. So, you know, a bedroom has 0, a living room has 2, kitchen also has 2, and both the living room and the kitchen need 1 square meter. So I've anticipated this because there might be different rules in different countries, or maybe we want to start trying to drive for a higher standard where other rooms that aren't living rooms also get to have sunlight and get that measured. You could do this in Excel if you wanted, but I really hate Excel, so I've just done it in Grasshopper. In it comes, so here we go. If we just switch that one off so we can see what we're doing, now we can look at the results. So the first thing it'll do, it'll show you the compliant and non-compliant meshes. So that one is red because it's non-compliant. And same thing goes for the compliant and non-compliant room groups. Now if, for example, we did have a higher standard where it was not just the living room but perhaps some other rooms, then a compliant group would be one where all the rooms were compliant, whereas a non-compliant group may have no rooms compliant or a mix of compliant and non-compliant. From there, we can output sentences in English which describe what's happening. So, room number 6 of type living of apartment 0104 complies with 7.61 meters squared, having at least 1 meter squared with 2 or more hours of sunlight between 9 and 3. Whereas a negative of that is room 00401 of type living of apartment 106 does not comply due to only 0 meters squared, having at least 1 meter squared with 2 or more hours of sunlight between 9 and 3. Alright, so if we change that around and instead of only getting the living rooms, we had all the rooms. The way to do that would be to feed through this geometry. Hang on, let's turn the lock solver on first so it doesn't start computing before we're ready. Let's get the geometry, so that's the room basis that we're analyzing. Plug into geometry. And we're going to plug these in directly. So we can plug this into names. Types can be and groups can be this one. Alright, turn the locks over. Actually, why don't we pretend that we care about bedrooms? Let's say bedrooms have to have 2 hours of sunlight as well, and they also need 1. Let's just make it easy. Same rule. Okay, so let's have a look at the results. So we can see that these living rooms are probably okay, but some of these bedrooms, well, maybe there's a borderline, these are a definite write-off. And let's have a look what it says when we actually look at the results. So we'll switch off the view that has meshes, and let's have a look. Compliant meshes, there we go. So these are the ones, those rooms themselves are compliant. And these are the meshes that aren't compliant. Whereas if we go to the whole apartment view, then these apartments are compliant and these ones are not. Okay, so look, in review, the main problem I've had here is that the actual compute time to be able to handle a large data set in this node is really long. How long does it take if I run all of the living rooms and just the living rooms and not the other ones? Select objects, extract room bases. So it did eventually finish, but it took 4.9 minutes to finish. Compare that to some other ones, like, you know, the nodes that we wrote here. Well, 152 milliseconds or 53 milliseconds. That's quite a long time. Alright, what happens if we do both the bedroom and the living room? 14 minutes. Now, even though we're only assessing bedrooms and living rooms, I'm going to go nuts and see how long it takes to do all the rooms. Alright, 35 minutes to do the whole building. Does anybody have a good workaround for this? Maybe it's just that my computer is quite old and slow, and on somebody else's machine it'd run a lot faster. Or maybe we need to somehow get the process happening outside of Grasshopper. If you got any ideas, let me know in the comments or reach out directly. And so by using just a little bit of Python, we can modify an existing Ladybug component and optimize it for mass production. All we had to do was just put in some data trees and for loops, and from there we can maintain a complex data tree coming in and have a data tree coming out without all that data just getting mashed together by the off-the-shelf node. Now, I don't mean to put down the off-the-shelf nodes. They're great. I mean, thanks so much to the Pollination team for making them in the first place and making them free and open source so I can do this kind of thing. I think there's a great potential here to re-rationalize the rest of the Ladybug suite and also the Dragonfly and the Honeybee as well. I tried doing this kind of work a few years ago with the sustainability team, but look, they were such off-the-shelf ideologues, they really discouraged me from actually coding or innovating, and it was a disaster. But look, I'm open to trying again. If I can find a more progressive team which has better resources, better organized, we could go really far with this. You know what? I think we could even start to use AI. And I don't mean in a really cliche way where some idiot types into GPT, oh, I can use AI. No, I mean actually writing machine learning algorithms from scratch in Python. From here, we will be able to turbocharge this process. So we have a generator and a discriminator, and we have a feedback between design and analysis so that we start to optimize for the best designs before it goes into Revit and the documenters start locking in too many other things that it's impossible to make any fundamental change without a great cost to the architecture company having to rework everything. I was talking to someone on LinkedIn the other day about AI and sustainability because he was pointing out how much energy the data centers use to, process pictures of cats, and cats were environmentally destructive, the amount of native animals they kill, but I love Tango and I keep her inside. I was trying to explain to him how in AEC we're starting to use AI and it's kind of inevitable, and how I would like to start getting sustainability metrics into that at the early stages rather than it just being something that maximizes profit for developers. I think beyond the AEC sector, some people understand that there's things like passive design, but they don't really take into full account that in the future, as the planet cooks, that's not really going to cut it on its own anymore. Like, you think you have some shading that works in the summer, because the sun's at a steep angle, but what happens another time of year when it's really hot because of global warming and the sun's at a shallower angle? The shading's not going to work anymore. There must be so many things like this that we have to take into account. Thanks for watching. See you next time.
On the next episode, I don't know yet. Maybe some sort of fancy shiny geometry thing, because that's what gets more attention.